Welcome back to the Optimal Experience. If you have spent any time in the PC gaming space recently, you have undoubtedly seen the endless stream of complaints regarding graphics drivers. It is incredibly frustrating to invest in high-end flagship hardware only to suffer from black screens, stuttering, and system crashes. But why does this happen so frequently on modern systems? How is it possible that a brand new driver update can actually make your performance worse? And perhaps most interestingly, why do we rarely see these complaints coming from gamers running custom Linux environments? Today we are looking under the hood of GPU software architecture. We will break down exactly why modern drivers struggle in the Windows ecosystem, how performance regressions actually happen, and why the driver experience on Linux is fundamentally different. To understand the problem, we have to first understand that GPU drivers are no longer simple translation layers. They are massive monolithic pieces of software containing tens of millions of lines of code. When you are pushing a modern flagship graphics card, the driver is constantly juggling dynamic power states, aggressive voltage boost clocks, and real-time shader compilation. The primary reason issues arise comes down to the environmental fragmentation. AMD and Nvidia test their new drivers in sterile, heavily controlled lab environments. But once released to the public, that software is thrown into a chaotic ecosystem. It has to survive overlapping RGB control suites, aggressive kernel-level anti-cheat software, custom motherboard BIOS versions, and heavily bloated background applications. Furthermore, the operating system itself is frequently the true culprit. A perfect real-world example happened earlier this year. A January 2026 Windows 11 security update caused widespread frame drops and massive visual artifacting for Nvidia users. Gamers immediately blamed the GPU driver, but the underlying issue was a Windows API conflict. Microsoft changed how the OS handled internal processes, which completely broke the assumptions the GPU driver relied on. This brings us to the concept of regression, the counterintuitive reality where a newer driver delivers worse performance than an older one. This generally happens for three distinct reasons. First, game-specific optimizations. GPU vendors continuously release day one updates tuned for major game launches. To squeeze maximum performance out of a brand new engine, engineers might drastically alter how the GPU handles memory allocation or shader execution. Frequently, a specific architectural tweak that optimizes a new release will accidentally break or bottleneck the rendering pipeline for an older unpatched game. Second is feature bloat. Modern Windows graphics drivers are bundled with incredibly heavy software suites handling video capture, streaming encoders, and AI noise cancellation. Introducing new background telemetry consumes CPU cycles and interrupts frame pacing, leading to lower 1% lows and noticeable stuttering, even if your average frame rate remains unchanged. Third is thermal and power interventions. Occasionally after hardware launches, vendors identify long-term thermal vulnerabilities. A subsequent driver update might silently introduce stricter voltage limits or more conservative fan curves to prevent hardware degradation. This subtly lowers raw performance to prioritize long-term stability. So why do we not see these massive driver complaints from Linux gamers? It comes down to a fundamental difference in how software is built, distributed, and managed. On Linux, particularly for AMD hardware, the core driver is baked directly into the Linux kernel itself, while 3D acceleration is handled by the open-source Mesa stack. Because developers from AMD, Valve, and the broader open-source community all collaborate on this code, it is heavily audited, incredibly lean, and strictly focused on translating graphics APIs directly to the hardware. It completely abandons the bloated proprietary control panels and background telemetry found on Windows. Then there is cohesive package management. When you use a performance-focused distribution like CachyOS or SteamOS, the operating system kernel, the graphics libraries, and the rendering drivers are all updated concurrently as a unified system. This entirely prevents the classic Windows issue where the OS updates automatically in the background while the GPU driver lags behind, creating a disastrous version mismatch. Finally, Linux users have immediate rollback capabilities. Regressions do occasionally happen on Linux, but modern file systems support instant snapshots. If a bad update breaks a game, rolling back the entire operating system to its previous working state takes seconds. The issue is instantly resolved locally, eliminating the need to wait weeks for a hotfix. Ultimately, software complexity is the enemy of stability. As long as Windows environments remain fragmented and bloated with overlapping software suites, driver conflicts are going to remain a reality for high-end PC users. Let me know down in the comments what your worst driver experience has been and whether a bad update has forced you to roll back your system. If you enjoyed this technical breakdown, please hit that like button and make sure you are subscribed to the Optimal Experience. Thank you for watching, and I'll catch you in the next one.